welcome to turn off the screens behind you. Otherwise it could get very warm. Okay. All right, so last time we talked about this nice problem that we call find max, and we looked at two different versions of this. So we're going to continue with some of that discussion and look at even harder problems, even more interesting problems. So let's get that started. Okay. All right, something is happening there. Oh. Okay. All right. So today we're going to expand our set of problems into something more, so that you can learn some new tricks today. Yeah. So let's quickly recap what we did last time. We said that problem solving involves two major things. One is you understand the problem, you better come up with correct solutions, and also you try and find efficient solutions. Both of these are integral part. It's if you don't have a correct solution, you're not going anywhere. But if you have a correct solution and if it's not efficient, well, it's still not very useful for people. So both of these are necessary in order for problem solving to work out well. So we started looking at this problem. I thought I removed all the animation on this slide. Darn it. So we looked at these two versions. One is the basic version of find max, where we said if you're given an array of size n, all we want to do is to find the largest in this array. And I think there's a chair back there. And there's a naive solution where you set up a for loop, or you essentially iterate over all the items in the array and find the largest item, right? This naive solution runs in big O of n time, because it makes essentially n minus 1 comparisons. And we actually went through some arguments to convince ourselves that this is the best you can do. It is optimal. There's no way to do anything better. Now this is the basic version of find max. Then we said let's look at a query version of this problem, where you are given an array of size n. It's fixed in time, it never changes, but instead of just asking to find the largest item, I'm going to give you different queries. And each time the query may be different, and each time the query will involve two numbers, I and j, and your job is to find the largest item between indices I and j. So your array may be very large, but you're asked a query about some portion of the array, and that portion is defined by I and j, and you'll be told here's the left end, here's the right end, find me the largest. Now again, here we are going to assume that the input is given to you only once, and it's fixed in time, but the queries are going to be many, they're going to be numerous, and each time it's going to be a different query. Clear? So this is what we looked at last time, and your job is to find the largest item in the sub-array starting from index I up to index j. Yes? Are you with me? Okay, good. So the naive solution says, hey, you want to search between I and j? I'll set up a loop that I'll iterate from item I to item j, and I will look at all those items and find the largest. No big deal, right? The only problem is, depending on where I and j are, the cost is going to be, can be very high. In fact, in the worst case, it can be as big as big O of n, because I could be 1 and j could be at the very end, and so you might end up spending a lot of time answering one query. So we wanted to see how to improve this. And we came up with an improved solution, which I'll quickly recap for you so that it makes sense. Well, by the way, that improved solution actually runs in constant time per query. Every query could be answered very, very quickly, but you had to do a lot of pre-processing in order to make that to work, right? Now, let me kind of remind you, well, I'll come back to this picture. So the general approach is you take the array A, you do some pre-processing, you sit and figure out a lot of things, and then when people ask you queries, you're able to answer like that, okay? Which is something that human beings also do, where if we know that there are going to be lots of queries, lots of similar queries, lots of similar tasks, we do some prior work and then set things up so that the incremental work when new queries come in is a lot less. So that's the general approach here. And so you pre-process the input, you create a data structure, which we'll just call generically a data structure B. And then for each input query, instead of searching through the original array, we'll search through this data structure called B. And this data structure will be organized in some smart way so that your queries can be answered quickly, okay? So we will stop looking at the original input because we now have a smarter data structure that will help us to answer queries very, very quickly. And so we'll somehow ask an appropriate query from this new data structure and respond more quickly. Now, the time complexity is different because we have a pre-processing cost that we had to deal with even before any of the queries showed up, right? Because we were creating this data structure. So there's some cost involved in these first two steps. So that's the pre-processing cost. And then we had to try and figure out what the query time was per query, right? And so if you look at all of this, then what you'll see is that, well, depending on how you do this pre-processing and what kind of data structure you use and so on and so forth, your cost keeps changing. So then the question is, how do I figure out which one's good and which one's not so good? And the answer is that it all depends on what your application is, what your constraints are, what your needs are. And so there is no one single answer. It just depends on your constraints. In general, what you'll see is that there is a trade-off between pre-processing time and query time. What does that mean? Well, before you ask any queries, if you spend a lot of time, then hopefully you can answer the queries very, very efficiently, very quickly. Or if you say, I don't want to spend any time pre-processing this, I'll just leave it as it is. Whenever I need something, I'll go and look through it. Well, then your query time is going to go up, right? So pre-processing time could be as low as 0 or as high as a lot, but your query time will depend on how much pre-processing you did and how smartly you organize this data structure. And so this is a kind of trade-off that we will be looking at. And you'll see that many problems kind of fit this description, fit this general setting where the input doesn't change, but your queries are constantly changing. And if that is the case, then you would have to think about what your best solution is. And so I'll go back to this picture here, which told us, which summarizes what our solutions are. The basic solution, there is no pre-processing. There's only one query that says, find me the largest in this whole array, right? So I don't need any pre-processing because the processing itself is pre-processing. And we know that it takes big O of n time, and we know it's optimal. We don't have to worry about trying to improve this. But the query versions, there are two versions. If you don't do any pre-processing, then this initial pre-processing cost is 0, or we'll just call it constant. But the query time is now big O of n because it depends on how big your query range is, right? So if there are k queries, then the time it's going to take is k times n. Yeah? On the other hand, if I do something smart and if I do a lot of pre-processing, I can bring down the query time all the way down to a small constant. Essentially, it'll be a lookup in a table. And then the cost simply becomes, if there are k queries, it's going to be k times a constant, so it's just k, plus the pre-processing cost. Now, how do we do this? Well, it's actually a fairly straightforward thing. We talked about this last time. Let's get there and look at this. Come on. Yeah, so this is the picture I showed you last time. If your input is this array, then you can pre-process it. There's some chairs here. You can pre-process it so that you build a two-dimensional matrix, and the two-dimensional matrix will have values, will have essentially the answer for any range that you want, right? Every possible range has a start point and an end point. There are n possible start points, there are n possible end points. For every possible range, I have an answer. I figure it out right at the start. Before anybody asks me any queries, I have it already, and it's all in this table. You just ask me a query, and I'll read out the right answer. It becomes a matter of lookup at that point. That lookup essentially takes you constant time. So what we've done here is to reduce is to spend a lot of pre-processing, but reduce the query time all the way down to a constant. Okay? So this is the kind of trade-off that we'll be looking at. No pre-processing, but high query cost, or lots of pre-processing and very, very low query cost. All right? Everyone okay with this so far? Okay. All right, so then question is, how do I do this pre-processing? Well, it's actually a fairly simple thing. You set up 2 for loops and you fill up that two-dimensional array I showed you, right? So for p equals 1 to n, for q equals 1 to n, you compute this array b, two-dimensional array b, and that's all there is to it. Now, in fact, we're not quite done, because how you do this is quite tricky. If you do this in a naive manner, then this itself could take you a high cost, because you're doing it from location P through Q. And if you just go and naively find the largest, then this step itself could cost you big O of n time. And so then the time complexity becomes n times n times n. So it becomes an n cubed cost. Is this clear? So if you don't do this carefully, the time complexity becomes very, very high. So even though there are only n squared entries in this two-dimensional matrix, if you don't do this smartly, your naive cost can be big O of n per entry in this array, and therefore the total cost can be as high as n cubed. And this is what we discussed last time. It turns out you can improve this if you apply some tricks, and those tricks can be. I did show this last time, but let me just go over it for those of you who were not here. Yeah. So here's where you essentially, when you want to fill up one of the entries in that two-dimensional matrix, you use the previous values to figure this out. So you don't go and recompute the whole thing. Instead, b of p comma q depends on b of p comma q minus 1. And so you figure out what the previous value that you filled in was, and you use that to figure out what the next one is. And there's a simple formula. Essentially, you have to look at the previous value and the next value in the original array, and then figure, depending on which one is larger, you may have to update your two-dimensional matrix. So there's a simple fix for how you do this computation. This computation is just that. So if I replace this statement over here, then I'll be done. And what you'll see here is that this calculation is just finding which of the two numbers is larger, right? And so therefore, this can be done in how much time? Yes? O of 1 in constant time, right? So if I can do this in constant time, essentially computing this matrix becomes big O of n squared. So my pre-processing cost went down from n cubed to n squared. Is that clear? But that didn't change the time for the queries because the query cost is just constant anyways. It's really, really fast. Okay? So it turns out you can do even better, and that's where we're going to head today. So this is the state of things so far. We have a basic version where we do no pre-processing, but our query costs are high. It's big O of n, right? The other version is I can spend big O of n squared, build this big whole table, and then my query cost becomes all the way down to a constant. The only problem is that the time for pre-processing is quite high. And what's also not so great is that I have to store all of this in a large two-dimensional array, and if I have lots of rows and lots of columns, this could be a cost that might be prohibitive for you based on what kind of a machine you have access to. So this is a high cost, but in contrast, the query cost is really, really low. Okay. So the next question we want to ask is, what if I cannot pay this kind of pre-processing cost? What if I don't want to pay that high a cost, but I'm willing to trade off and say, all right, I'll pay a little extra for query costs. It doesn't have to be all the way down to a constant. Let's make it a little bit higher. Okay, I'll pay a little bit more for each query, but I don't want to pay this kind of pre-processing cost. Okay, that's a trade-off that maybe you might need to make. And that's what we're going to look at next and see how this works. So how do we do a better trade-off between pre-processing time and query time? And also there's a pre-processing space cost. I mentioned this, your two-dimensional array is too large. So the big question is, how do I make this better? By the way, I'm talking too much. You guys are not interacting enough, so I'm soon going to make that happen. So let's look at a simple input. Yeah. So let's say this is an array that's given to you. Yeah. I made it small so that we can quickly do calculations in our head. There are only 7 items in this array, and you're allowed to pre-process this as much as you want, but I don't want you to do big O of n squared work. Okay? I don't want you to build a two-dimensional array and save all kinds of information there. I want you to do less pre-processing, but I want you to still do queries better than big O of n. Is that clear? So that's where we're going, and the question is, how do I do this? So well, just to make things clear, let's also put these indices here. So this is position 1, position 2, position 3, and so on. So we know that there are seven items in this array. Okay? So you're allowed to stare at this array, do whatever pre-processing you want, but I'm going to ask you a lot of queries. I'm going to say 2 to 4, or I'm going to say 5 through 7, or 2 to 7, and your job is to tell me as quickly as you can what the highest value in that range is. Clear? So question is, what do I do? I'm not allowed to put a large table. I am not allowed to go and search from scratch. What do I do?
You can try.
Sorry, go ahead.
No, you're good.
No, you start already.
No, I think.
Well, we mentioned this last time and it got shut down, but you could. This would be the n squared pre-processing time of just using the dot sort method, and then you can search for the last the j index, because that will be the largest value.
Right. So the reason we didn't pursue that solution was because I could sort it. I could sort this array and make it look like 3, 6, 7, 9, 11, 14, 21. But then I also have to remember what its index is. And then if I tell you, hey, find me the largest in the range 3 through 6, how are you going to search through this sorted array and figure this out? Right? You can't just look at the sorted array and figure that out. That's the reason why we didn't pursue it. Is that clear?
Yeah.
Okay, so we need a different approach.
You were gonna.
That's what I was gonna say. Could we start with indices and assorted values?
Could
Yeah,
we,
sorry.
well, the indices are sorted, I don't have to do any work for that, it's already 1 through 7 in that order, and the values, I can sort them, sure. So I could sort them and I'll know that the smallest one, 3, is at location 3, next smallest is at 4, next smallest is at 7, and so on. But how do I organize this so that if somebody asks me a question saying, find me the smallest between 3 and 6, what is the work that's involved? Right? That's the challenge. Any suggestions, any thoughts?
Could we put the array and their indexes into a hash map?
So we will not pursue hash maps in this problem solving session because hash maps are not a extendable solution. They work well because Java provides them. However, the hash maps have the problem that the hash function is not something that's well defined, and the worst case performance, if that hash function is poorly picked, the worst case performance can be much worse than anything that you have. In practice, it works well, but that's not what we want because we want to think of guaranteed worst case solutions that will perform well no matter what. Okay, that's why we will not consider hash map type solutions. Fine. So for now, let's just put that aside. We don't really want that.
Can
Yeah.
we make subarrays?
Sorry.
Can we make subarrays?
You can make whatever you like. The problem with subarrays is that in the end, I have to try every possible subarray. In that case, it just becomes my original 2D matrix,
Okay.
right? Because I have to say between 3 and 6, 4 and 7, etc.
You could store the array in a tree to like divide the
You
array
could
into
store the
sections.
array in a tree. Well, that was part of the title, so in fact you had a clue right there, and I'm glad you picked up on that. So really the answer is that you have to somehow use a tree. So the next question is, how in the world am I going to use a tree to store things and answer queries quickly? All right? So that's where we are headed. Any
have
thoughts, questions?
I think it's got an augmented tree where we can store at every node additional information.
Yeah, you're absolutely right. It is called an augmented tree, but I won't throw these terms at people here. So let me keep it simple, and just say that it's some kind of a tree, okay, with information in it. So here's what this tree is going to look like, and maybe you'll get some clues in this. I'm going to organize this as a tree. This is my tree. What do you see in this tree? Where are the items in the array, and where did they go in this tree?
At the bottom of the tree.
They're all at the bottom of the tree. They're all leaves in this tree, right? So the array elements, 21, 9, 3, 6, etc., are down here, right? And then we made it into this perfect binary tree, right? So these two are connected to their parent. These two are connected to a parent. These two are connected to a parent, and there was one short, so we had to do something there. Yeah. Let me get that off the. All right. Oops. What did you do? Okay. All right. So I've now put this into this nice looking tree. What do I do with this? So somehow I have worked in, I've stored the values here, right? I've also stored the indices. So I have 1 here, 2 here, 3 here, 4, 7, and so on, right? And then what happened in the tree above? Yeah.
Oh, it's taking two values and it's comparing them against each other, and the higher one will be pushed up.
That's right. So somehow you're keeping track of higher of two values, right? Now higher of what? What two values are those?
Those are the numbers in your.
Right. So, but what can you say about the general organization of this tree? What happens as you go higher and higher in the tree?
Find the largest number in the
Right, so it's collecting bigger and bigger parts of the array, bigger pieces of the array, and saying, here, I'll give you information about the largest in this part of the tree, or in this part of the array. Is that what you were gonna say,
Yeah.
Fair? Yeah. So for instance, this here, this node collects positions 1 and 2 and tells you the largest value. This collects 3 and 4 and tells you the largest value. This collects 5 and 6 and tells you the largest value. This collects 7 and whatever this was, a blank, and tells you the largest value. And then when you go one more level up the tree, this says, I am going all the way from 1 through 4, and that guy there is the largest, right? That's all you need to know, it's the largest, yeah? And same thing over here, this is all the way from 5 through end, and the largest is 14. And then what about up at the root of the tree? It's the largest in the entire array, right? So at each node, we have that node overseeing a large chunk of the array and keeping track of what is the largest in that part of the array. Now, this is useful because there are ranges keyed into each of the nodes, right? So if I asked you, hey, tell me what's the largest in 5, 7, well, you could find that in the tree and tell me the answer that it's 14, right? Or if I say 3, 4, you'll eventually find this node and you'll tell me it's 6. Now, is that faster than actually going through? So by the way, you need to have the imagination to scale this up and think that this tree is very, very large. Is that clear? Here it's a small tree, but you need to scale that up in your head. Fine? Now, if there are n items in this array, what is the height of this tree? If there are n items in this tree, how many nodes are here as leaves? Roughly n, right? How many are here in this level? Sorry? N over 2, right? Because every pair kind of got a parent, a single parent, right? So essentially it got cut down by a half. So if there are n nodes here, roughly speaking, there should be n over 2 here. What about here? N over 4. So if it has to go all the way up to 1, how many levels are there?
Log of n base 2.
Log of n, not yeah, because every time it gets halved, and logarithm to the base 2 is essentially how many times you keep cutting it down by half before it becomes 1, right? That's what logarithms are. Is that clear? I don't see people happy. Did log of n throw you off already? Come on, yes, no, tell me. I can tell you how to think about this.
Quick question.
Yeah.
I'm not sure if I'm seeing it, but what if you wanted to see between 1 and 6?
Yeah, we'll get there, so start to think about it. Great, you're asking the right question, but I'm not telling you the answer yet. Yeah. So, back to log n. Everyone clear about why the height is log n? Yes?
Yes.
Okay, all right, fine. So, so as he pointed out, some ranges are great because the answers are right there in front of you. Others are not. Well, let's not worry about those ranges for now. They're annoying. They don't. The answers are not there, but we may have to put in more work. Let's not worry about that for now. Let's look at the ones that are easy and can be looked up right in this tree. Okay. Now, for the ones that are in the tree, are you clear about how to do the search? That's the first question I'm going to ask. So if I gave you some range, let's say 5 through 7, how are you going to find it in this tree? Are you clear about this? Where do you start? Where would you start? You start from the root, right? And then you say, oh yeah, have I found the range here? If not, I have to decide whether to go right or left. How do you know you're going to have to go right or left?
Because each node has the information, you have one before and then you have 5 to 7.
That's right. So if I'm looking for 5 through 7, right? I'm going to start here, and well, 1 through 7 is not 5 through 7. That's pretty clear. So then I have to decide, should I go this way or this way? I look over here, and this says 1 through 4. Well, that's not part of 5 through 7, so let me go here. And then when I get here, it says 5 through 7. That's exactly what you're looking for. So here's your answer. If instead I'm looking for 5 through 6, well, I'm still in the same ballpark, and I am going to then look through the 2 children and decide which way to go. So by looking at the 2 children, I can figure out whether to go right or left, and so I can search this tree. It seems to be well enough organized that if the range is there in the tree, I can find it. It's just like doing your binary search trees. You're familiar with those, right? So therefore, I can search this tree for things that are in the tree. But yeah, there is a problem with things that are not in the tree. We'll worry about that in a few minutes. Now, for things that are in the tree, how long does it take me to search it?
Log of n.
It's log of n because
Tree size.
that's the height of the tree. And how do you know height of the tree is enough for the search? How do you know I don't have to go and look at every node in the tree?
You're skipping.
Because it's ordered.
We are skipping the unneeded nodes.
How do I quantify that? How do I know that that number will become log n?
You choose one branch and it gets cut in half each time.
Well, the right way to think about this is, I start at the root of the tree, and the root of the tree is at height log n from the leaves, right? And then it says either go left or right. So every time I step down 1, so the node I get to is 1 step closer to the leaf, right? And so therefore, each time I'm going down the tree, and in log n steps, I'm going to get to the leaf, because that's the height of the tree. Is that clear? So therefore, I am never going to make more than log n such comparisons. And therefore, if it's there in the tree, I can find it in log n time. Is this clear? Okay, so I've now, I haven't really told you how I'm going to create this tree, but I've magically shown you the tree, and if it's built, then I can find things that are in the tree. Clear so far? Okay, we still have a little bit more work to do. So let's see here are some of the ideas that we used. The first idea was we're going to organize this into what's called as a balanced binary tree. And its height, we know, based on our discussion, that it's log of n, right? Good. So the first idea was, let's, instead of this 2-dimensional array or a 1-dimensional array, let's build a tree. That was the first idea. The second idea was, put all the original values in the leaves of the tree, but in the right order from left to right. Right? That was idea number 2. And then we said, oh yeah, we're going to turn this into a complete binary tree built in a most natural way. Here's the third idea we used. The intermediate nodes here have some nice information. What information is that? Well, it's got the range of values, range of indices that it covers, right? And it also has the largest value in those range of values in the array, right? So there are two useful pieces of information which we know is valuable for us. So that was idea number 3 in this organization. And then we have one more idea where we stored in this the maximum in that range, in the subtree. Well, I already mentioned that there. So we're storing both the maximum and the range of indices that it covers, and we've organized this into a nice tree. And the height of the tree is log n. All this turns out to be useful in order to answer queries pretty quickly. So I'm going to give you let's zoom into one of these nodes. Doesn't matter which one. If you go and look at any of the nodes, this is what it looks like. This looks like any node in the tree. It has a left child and a right child. Any node in the tree has some range, A through B. I don't know what that range is, yeah? And it has a maximum value stored somewhere. And it has two children where on the left side I have A2 somewhere in the middle, right? And then that middle all the way up to B. That's how you split the range, right? And this may have a maximum value of P, this may have a maximum value of Q. Well, this one's going to have the larger of those two. That's what we know. So here's a snapshot of any node in this humongous tree. Is this clear? So all this turns out to be useful in understanding what this tree looks like and how we're going to do the computations. So therefore, if we ever get to this point in our search, all this information will help us to figure out whether to go to the left or to the right. You with me so far? Okay, so that was the snapshot of any single node. Now this M value tells you where to split, and we're going to take it somewhere roughly between A and B, midway between A and B. So we're going to do A plus B divided by 2. Well, we'll put a floor here and a floor plus 1 for the two intervals, right? You okay so far?
Yeah.
Okay, great. So that's how we're going to organize the tree. This gives us enough details, and we know exactly what we're doing. So how did this become an improved version? Well, this became an improved version at least for the nodes that are in the tree, at least for the ranges that are in the tree, because anything in the tree, I can pretty much find it in log n time. Because I can start at the root and work my way down, and sooner or later I'll find it, right, if it's in the tree. So that's a good place for us to start, and so therefore, I've just shown the tree all over again. Essentially it says this is an improved version because I have now reduced the query time to log of n. But the question is, how much time did I spend building this tree? Because remember, building the tree is pre-processing, right? If I build the tree right at the start, then my queries hopefully will go faster. At least some of the queries will go faster. So how do I build this tree? Any thoughts on how you can do this? Or what the time complexity of building such a tree would be?
Well, it's going to be bigger than n, for sure.
It's going to be bigger than n. How much bigger than n? 2n? 4n? N log n? N squared?
N squared, maybe.
Okay.
What the other friend is?
If it's n squared, then it hasn't saved us much. Then our purpose is lost, right? Yeah, well, in fact, we spent n squared in building this thing, And yeah, but you know, our query cost went up from what used to be constant to log n. That's not that great then. Well, let me also ask you, how much space did I use here? Was it n squared?
No.
Remember, there are n nodes here, n over 2, n over 4, n over 8, and so on and so forth.
And log n.
Log n?
So n log n is a good estimate because there are only log n levels, right? And the largest is n, so n log n sounds like a reasonable estimate. But actually, it's n plus n over 2 plus n over 4 plus n over 8. This is what's called as a geometric series. It quickly converges, and in fact, when you add this, it turns out to be less than 2n. Now, how did that 2n come about? Well, it turns out that there are reasonable ways to think about this. Let's assume that the width of this room is 20 feet. Okay, and I start from here, and in 1 unit of time, I cover half the distance. Okay, so in the first unit of time, I would cover how much? 10 feet. So I'm here. In the next unit of time, I'm going to cover another half. That would be 5 more. Another half in my next unit of time. I can keep doing this, and what does it converge to? I will eventually get, well, I won't quite get there, but I'll get close enough. So n plus n over 2 plus n over 4 plus n over 8, blah, 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 is still less than 2n. Okay? And it all comes from this picture in your head. If you can think about it, it's quite easy to figure out. All right? There's also a formula for geometric series. If you go look up your college algebra book, it'll remind you again. Fine? So therefore, there are only how many nodes? Yes?
N?
How much did we just say? This is n, so therefore how many? How many nodes in all?
N log n.
Sorry? 2n, at most 2n, because n plus n over 2 plus n over 4 plus n over 8, I'm doing n plus n over 2 plus n over 4 plus n over 8 and so on. That whole thing, that series is less than 2n, right? So therefore, there are at most 2n nodes here, and so therefore the amount of space I used is
N?
big O of n, right? So that's good, that's good. That's actually not too bad. Now we've cut down our space usage. Instead of a 2D array, which takes order of n squared space, it's now down to big O of n, right? Well, but the time it takes to build is still unclear. We're going to put that off till later. It turns out that you can actually do this very, very quickly. But we'll discuss that at the end. Fine? So it turns out building this can be done quickly. The amount of space that it uses, the pre-processing space, is small. It's only big O of n. And we are able to answer many, many queries in big O of log n, because if it's there in the tree, I can find it. So now we're left with only one task, and that is, what about those things that are not in the tree? Okay? Are you fine so far? Is all this clear? All right, good. So let's move on to the next thing. For this, we need to kind of understand how we answer queries. Okay? So remember, the way we answered queries, we always started at the root, and then we make a comparison. And the way we make a comparison, we start at some node. We carry around this range that we want to work with, the I and j. So think of u as the node in the tree. It is any generic node in the tree. We start with the root. Okay. So we ask this query: does the node u contain the interval I, j? That's really the question we'll keep asking. If it is, then we're done. We'll just report it and say, whatever is the maximum that we've stored in that node, we're just gonna report it. Clear? So if it's that interval, then we'll just report the maximum value that's stored in that node. Otherwise, there are two things that could happen. One is something could be less than and something could be greater than. And we have to decide whether to go left or right. And that's the question that we have to answer here. So what is the condition that I need to decide to go left? What is the condition I need to decide to go to the right? Anyone? Yeah?
Check I with the, like to check I with the,
I with?
the max of the left child.
Okay, good, yeah. So this is the interval we are searching for. And remember, every node has stored an interval, right? Has stored a left end and a right end. We have to decide where I and j kind of fits into that picture, right? If it's exactly equal, then we're done. If it's not, we have to decide whether to go left or right. And there's a simple consideration here. We're going to check whether the right end of the interval goes from, if that, actually I should just say interval goes from I through k, where k is smaller than j. So therefore, it's more to the left end, and therefore, which way would I go if this were the case?
Left.
I would go left, right? Because here, the left end matches, but the right end is smaller than the interval, than the, what did I say? Yeah, the right end. I did make a mistake here. Yeah, I screwed up here. Anyways, that's actually wrong. What I've written there. I'll fix it and send it to you. So we really need to check if j is smaller than the right end. Only then this works out. So yeah, I have to rewrite this. But there is a simple condition that you have to figure out. Okay. Once you figure it out, I am going to ask the same query for ij, but with the left child of node u. Otherwise, I'll go to the right child. Is this clear? My apologies for the wrong condition there. I have to rewrite this condition. Shall we try and figure this out, this condition? All right, let's see if we can rewrite this statement properly. So we have else. Oh, fact. We're going to say else if. Does anyone want to help me with what this condition is going to look like? Remember, we are trying to rewrite this sentence here, and it's wrong there. So don't look at that.
U dot interval.
U dot interval. Okay, dot RT, the right end of the interval is you want to compare it with, yeah, what do you want to say?
What's U?
U is the node that we're currently looking at.
Okay.
Right? We're somewhere in this tree, we're at node U, and we're looking at the information there.
Okay.
Remember, at each node we have a range, right? a left end and a right end, and we have a max value. Now, if that range matches exactly what we're looking for, then we just report whatever is there. We're done. But then, if it's not, I have to decide whether to go right or left. And the question is, what is the condition that I need in order to make that happen? Did you tell me what to say here?
It's IK because we go from the beginning to the center that is K, right?
No, remember your IJ is smaller
The
than
query.
what's in the
Yeah.
node. So how do I say this?
Is it case greater than I?
It's no.
Where are we
We're
getting
looking at the.
Sorry.
Case,
Where
I
are we
mean,
getting
Right. So that's why I said forget that. Come up with
Okay,
just
so
come
we're
up with.
about K.
Could
Oh,
be any
okay.
number.
Let's rewrite that sentence. It's wrong. We know it's wrong.
Okay.
You might need K. Yes.
If the right interval is less than the ask node,
Less than
the ask node, start of the ask node,
start of the
ask node, like
Of you.
range, the range which is asked. If the start
you
is
mean,
less than the right,
is greater than J. Is that what you're saying?
it should go to
It should be the
Let-
the
it should be
J
less.
So
is the
remember,
right.
you're now at a node somewhere up in the tree, and as part of that interval that's stored there, somewhere is I and J. Okay? And your job is to figure out whether to go right or left. Yeah.
If check if I is less than the left child's node J.
Right. Yeah. Well, isn't that the same as saying if the right? So you really have to look at the midpoint, is what you're saying, right?
Yeah, to like check that I have the
Yeah.
left.
So right. So let's try and take care of that.
We just
then.
change that to left, won't it work? Change
Okay.
this to dot left.
So let's say we also store the midpoint then,
Midpoint?
right? If the midpoint is greater than J, then we know we have to go to the left, right?
Can we
Yeah.
specify which other branches we're trying to look at right now? Because,
Well, it doesn't matter, you can specify that from the condition. If it's greater than J, then I have to go to the left. If it's less than I, then I have to go to the right. Right? Because we are assuming that we can find the whole range somewhere in this tree.
Wouldn't you need the midpoint of I and J and not of the nodes interval?
It's the same thing, we're going to assume that the midpoint is what was used to separate the left child and the right child, okay? So I'm going to say if it is greater than J, then I know for sure I have to go to the left subtree, okay? Because the left child is going to go from I, or it's going to go somewhere all the way up to the midpoint of that range, right? And so if the entire interval J is on the left side, then I'm going to go to the left subtree. So this condition here will get replaced by that. So then I am going to find the find what? Find max query. Pardon my writing. And here I'll have I and J and U dot left child. Okay? So essentially it's saying, should I go look at the left child or should I go look at the right child? If that entire range is on the left, in the range for the left child, then that's where I need to go. And I figured that out based on the midpoint value. Is that clear? So the next one is going to be somewhat similar. In fact, I don't even need a condition. I can simply say else, even if you don't have this condition, it's going to be find max query I comma J comma U dot right child. But let's put that in anyways. So it's going to be U dot interval dot left if this is less than I, sorry, wrong. Yeah, this is midpoint. If it is less than I, if the midpoint itself is less than I, then the whole range is on the right side, and so then I go to the right subtree to do the search. Is that clear? So then it's going to be all of this, but with u dot right child. Is that clear? Yes? No?
No.
No?
No.
Which part?
For example, I'm thinking of the example 1 through 6, right?
Yeah.
If we were to go
Yeah.
to
So
either,
again, we are focusing first on ranges that are in the tree.
Okay,
I'm going
okay.
to tell you in a short bit what to do with ranges that are not in the tree.
oh, so this is
Let's
for
focus on
only.
the-
Oh, okay, okay, okay.
Only when if the whole range is somewhere in one of the nodes in the tree.
Okay, I
The
thought that
easy
was for
case.
the other one.
I've
Never
not
mind.
quite gotten to the hard case.
Got it.
Okay, fair enough?
Yeah.
Okay. So far so good? All this is fine then?
Yeah.
Yeah, if you're already thinking of the next case, go ahead, that's good. That's the hard part, and you should be thinking about it. I'm giving you more time to kind of come up with ways to deal with that. Are you okay with this so far? Yes? Okay, excellent. So that's how you fix this. This is actually incorrect, and we're at least set with this. Oops, sorry. My animation is a mess. Okay. How do I fix this? All right. So here's an example. The picture is a little messed up. I'm only showing a part of the tree. Let's say I'm searching for the range 5, 6. The way this code will go, it'll start at the root of the tree. This is the vertex u now. It will compare 5, 6 with that, and 5, 6 is not 1, 7. And now you have to decide whether to go this way or this way. It will compare it with the midpoint. The midpoint is 4, and since I, that's the left end, is 5, is already bigger than the midpoint, so therefore I know that I have to go to the right side. Clear? So over here, the midpoint is 4 for that first node, right? And 4 is not bigger than j, but 4 is smaller than I, which is 5. Is that clear? So therefore, I would go to the right child. Therefore, this guy here is not relevant. I'm never going to look at it. And so I'm going to cross it out. Come on, yeah, there you go. We haven't quite gotten to this. My animation got messed up, but that's the final picture. So I go to the right child. Again, I'll compare 5, 6 with this. It's not 5, 6, so we haven't found our node yet. But we know that the midpoint is 6, and 6 is bigger than or equal to j. So actually, I need bigger than or equal to. Right? Are you okay with this? Okay. So therefore, the first condition is met, and so it goes to the left child. So all of this is ignored. Now, when it gets here, it'll check whether the range is exactly what we're looking for. That's our first condition. Is it equal? And that's that, and so that's where we'll stop. So if the range is in the tree, we'll just march down the tree and eventually find it. That's the key so far. All right? Now, all of you are wondering what in the world we're going to do if it's not in the tree.
Yeah.
So what do? I don't have slides for it because I didn't finish making it, so let's get started here. How do I clear everything? Clear, okay, good. So let me put back a tree that we can work with. Oh yeah, I can explain some things here. So, in general, searching for a node in the tree is going to involve things like this. You're going to dance either left or right, yeah? And eventually you're going to find it somewhere in this tree. This is for nodes that are in the tree already. So some places you'll make a left turn, some places you'll make a right turn. You'll go to the left child or the right child. And so in the end, it's going to look like this. Now, in this process, whenever you go to the right child, you'll see that all the left subtrees are simply ignored. And they may be large trees over there, lots of nodes, but you're never going to go and look at them because they're not relevant. Is that clear? So those are the red things I've marked here. They're just subtrees that don't need to be looked at, because at this point, your comparison said go right. Actually, I should have done it here as well. I forgot to put that in. Yeah, I have that as well. So you'll see that these are all the subtrees that I'm essentially going to ignore as I go down my tree and search. And then there are subtrees of this too that I will not be searching, and even those are going to be ignored. So a whole bunch of things that essentially get ignored, and that is very useful because otherwise your search becomes too expensive. In fact, this is what makes the cost of the search to be log n. Now, we're going to use this picture in order to understand what happens when we are searching for a range that's not in the tree. All right, so let me go to the let's use this tree. So let's say we want to search for what do we want? Say 4 to 6.
3, 6.
3, 6. You want 3, 6. Okay, 3, 6. So let's say we want to search for the range 3, 6. All right. So the way we're going to go about this is we're going to isolate this problem to first search for 3 and then search for 6. Okay. So how do I locate 3 in this tree? Well, it's a relatively easy matter. 3 is definitely in this range, but is 3 over here or over here? For that, I just compare the midpoint, and it tells me that 4 is the midpoint, so therefore 3 must be over here. Okay? Then I again look at the midpoint and decide whether I want to go right or left. So therefore 3 is over here. And then again, I make a look at the midpoint, and I know that my 3 is on the left subtree. So therefore, my path has gone something like this. I started at the root of the tree. I went, I went left, I went right, and then I went left. This is what I did. And in each case, I ignored a bunch of so I ignored the move. All right, I'll just do it here. In each case, I ignored this right subtree, I ignored this left subtree, I ignored this right subtree, and I ignored both the right and the left subtree over here. Okay, so I've just drawn those in order for you to understand that those were parts of the tree that we didn't look at. But we've located, so far, we've located 3, which is somewhere, which is over here. Next thing I'm going to do is do the same thing, but for the right end of of the range that I want.
Can I ask a question?
Yeah.
So am I looking for 3 or am I looking for the max between 3?
I haven't gotten to the max yet. For now, all I'm going to try and set this up for you. So after that, you can see what exactly how good. So I'm only using the range at this point. I'm not using the max values so far.
Okay.
You'll see later how those factor in. Okay. Then I am going to look for 6. Remember, I'm looking for the index 6, not the value 6. Is that clear? Because I've been asked a query that says between index 3 and 6, find me the largest. That's the query, right? So I'm going to try and locate 6 over here. And again, I started the root of the tree, and I go right because 6 is on the other side between 5 and 7, and then it's on the left side at 5 and 6, and then it's on the right side at 6. So this is where I'll find 6. And again, in each of these cases, I have discarded or not bothered to search good chunks of the tree that are also there. Is that clear? So I have located 6. 3 is over here. 6 is over here. And my job is to find the largest value between 3 and 6. Now, I could just go and search along the leaves and give you the answer, but then it essentially becomes as good as searching in the array, and that's too expensive, right? So I need to do something with the tree and not with the array, and so therefore, I'm going to walk up the tree and figure this out. Now, yeah, so let me also draw this picture, the things that I've ignored here. If you recall, I'm ignoring this part of the tree, I'm ignoring this part of the tree, and I am ignoring these 2 parts of the tree, and of course over here as well. Okay, these are the parts that I've ignored. They're not relevant, but eventually they'll become relevant. Okay, now I've located 3, I've located 6. I want everything in this tree between 3 and 6, and I want the largest. Now the question is, how do I do this? Well, let me start from 3, and I walk my way up. If this one here is 3, what is the range for that node? We know that the range for this node is 3, 4. The range for this is 3, 4. Now, 3, 4 is part of what I want to search. What about this one here? This is 1, 4. Okay, and this here is 1, 7. Now, the range here and the range here is not quite what I want because it has things that are not part of my of the range that I'm interested in, which is 3, 6. Okay, so the only 2 nodes that are particularly relevant are this guy here and this guy here. All right, now let's look over there. 6 is sitting here, so whatever is here is relevant. This guy's range is what? It's 5, 6, and 5, 6 is relevant, right? So I'm going to circle that. That's relevant. This guy here is not, because the range here is 5, 7, and the range here is 1, 7. Okay, so effectively the only relevant nodes here are this guy here and this guy's here. Okay. What we're going to do is look at these nodes because they become quite important. And what does that mean? Well, what you'll see is that even though we ignored this entire subtree here that was hanging, all that is part of things that need to be considered. Same thing over here. All of these are part of things that need to be considered because they're all in the range 3 through 6. Same thing over here. All this is part of stuff that needs to be considered, and same over here. Nothing else is of relevance. Okay? Everything else is already accounted for in these subtrees that we're looking at. So it turns out that our answer for the largest in 3, 6 is the largest in this subtree, in this subtree, in this subtree, and in that subtree. So we walk down these paths and find all the things that are hanging on an appropriate side of the tree and find the maximum, keep track of all of that, and report the best. Okay? And the total amount of work that you do is essentially find two paths that are of length log n, and for each one of these you have subtrees hanging off of them. For each of those subtrees you pick the largest one, which is already stored in that subtree at the top, and you just find the largest. Now all of this looks complicated, but essentially what it's saying is, in order to search for the left end of our interested interval, this is 3, 6, in order to find the left end, all the things that are hanging off on this side, those are relevant, right? And then all the things on the right path that are on this side are also relevant. And so those are the only ones I have to take into account. And since they are subtrees and they've been pre-processed, I just need to pick up the largest in those subtrees and report the best. Is that clear? Kind of. How am I doing with time?
We're at time.
I'm out of time?
Just
All
in
right,
time.
just in time, okay. Yeah, I should stop right here. But this is